At ANSTO, we investigate materials behavior in extreme environments in order to ensure safe and reliable operation of the current and the next generation of nuclear reactors. When talking about extreme environments, we are talking about a combination of various environments, such as high temperature, corrosion, radiation, and mechanical load acting on a material at the same time during operation of a nuclear system.
So when we talk about extreme environments, we are talking about extreme in-service operating conditions combining different environments and acting on a material at the same time. For example, in engineering systems such as nuclear reactor, we can have mechanical load, radiation, corrosion, and high temperature acting and affecting material and its behavior and its degradation at the same time. So we know that this kind of environments are expected in nuclear systems, and we also know that material and their performance is one of the greatest technical obstacles to improving the safety, efficiency, and economy of the current nuclear systems. So we know that understanding of materials in extreme environments is important. However, doing this kind of combined testing in laboratory conditions is not easy. However, ANSTO is a home to Australian nuclear expertise and custodian of sovereign nuclear capabilities, including the research reactor, is uniquely positioned to investigate the performance of materials in extreme in-service conditions, for example, combining high temperature, radiation, and corrosion environments. As I mentioned, we operate nuclear reactor, we also operate accelerators and recently commissioned hot cells, which all help us to build understanding of materials under irradiation conditions. We also operate a number of chemical laboratories where we do a lot of corrosion studies, and also we operate high temperature laboratories where we do a lot of high temperature testing. However, most importantly, of course, we have in-house knowledge and expertise coming from all our engineers, scientists, and physicists working together to build this holistic understanding of materials in extreme environments. And this is particularly a job of Reactor System Research Program, which aims to understand the fundamental and applied aspects of combined environmental effects on materials, which are going to be used in the future generation of the nuclear reactors. When talking about understanding of materials behavior, degradation, and ultimately failure, we need to first realize that materials are multi-scale systems, and we thus need to gain understanding of materials at multiple physical scales, from the atomistic scale to the macroscopic scale, and also over different time scales, from less than nanosecond to many decades. Let me put it in a different way. Knowing that a piece of material has failed at the macroscopic scale has a rather limited value without really understanding underlying failure mechanism, which is often connected with the atomistic structure of the material. And here ANSTO's core infrastructure can help us, as we can use our neutron synchrotron and microscopy techniques to probe the material at different scales in various environments, for example under load or under high temperature or even under irradiation. And we combine our state-of-the-art multi-scale experimental techniques with multi-scale modeling approaches, where we can simulate materials response from atomistic scale to the macroscopic scale. And this is very important because this helps us to develop fundamental understanding of materials behavior, and we therefore use our experimental data to build and validate physically based or semi-empirical or even machine learning based models, which then help us to predict materials behavior in extreme in-service operating conditions of a real-world engineering system. Let me now show you some of our recent work on molten salt corrosion of alloys, and specifically on molten salt corrosion of welds, because a lot of effort has been invested into the development of materials which can withstand molten salt corrosion. However, much less effort was spent on understanding of performance of welds in molten salt environments, and welds are very important because that's where the material tend to fail the most often. And this work doesn't have to relate necessarily to molten salt reactor system, it's related to any molten salt based energy generation or energy storage systems. For example, concentrated solar thermal systems sometimes utilize molten salt as both energy transfer and also energy storage medium. So in this example, we are going to be looking into nickel moly-chromium alloy, which was specifically designed to withstand molten salt environment. And here comes this multi-scale understanding of materials. So even though the world metal and the parent metal have similar chemical composition, when we look at the microscale, they are significantly different. While the parent metal contains a large number of small crystallites, the world metal contains significantly larger crystallites. And this has consequences not only on mechanical properties of the parent and the world metal, but also on the corrosion behavior, as we will see in the following slides. Let me now show you some of the results, but before jumping into the discussion on molten salt corrosion performance of the world and the parent metal, we have to test the strength of the material, because if the strength of the material is not satisfactory, there is not even point doing molten salt corrosion testing. So we have extracted small specimens from both parent and the world metals and simply loaded them until they fail. And from the results on the left hand side, you can see that actually the world metal is stronger than the parent metal because it fails at higher applied load. So this is at the macro scale, but if we want to understand this behavior, we have to always look into micro scale. And we found here on the right hand side, we can see that we have in the parent metal, we have these particles which are failing and propagating the crack. While in the world metal, these particles are significantly finer. So, and this is one of the reasons why the world metal is actually stronger than the parent metal. So this is great. We found that the world metal is strong enough, but this test tells us nothing about molten salt corrosion performance. So in the next step, we're going to do a molten salt test and find out whether this weld can be used in the molten salt environment. After confirming that the strength of the world metal is satisfactory, we can move to molten salt corrosion testing. Again, for this test, we extracted small specimens from the world metal and from the parent metal, and we submerged these specimens into the molten salt at 750 degrees for 1000 hours. We measured the mass of the specimens before and after the exposure to the molten salt, and you can see the results on the right hand side. From these results, you can see that the world metal specimens actually lost less of their mass when compared to the parent metal specimens. This simply suggests that actually the world metal has better molten salt corrosion performance than the parent metal. This is again at the macro scale. If we want to understand this result, we have to look into the micro scale. And indeed, we found that the microstructural differences between these materials is the main reason for this observation. So we found that the large amount of interfaces between variously oriented crystallites in the parent metal accelerates the dissolution of the parent metal into the molten salt. While in the world metal, we have significantly larger crystallites, which leads to significantly smaller amount of interfaces. And that's why the world metal has better molten salt corrosion performance than the parent metal. So from these results, we found that the world metal is not only stronger, but it also has better molten salt corrosion performance and can be thus safely used in molten salt environment. After finding out that the world metal microstructure offers better molten salt corrosion resistance and also higher strength when compared to the parent metal microstructure, we have decided to team up with our colleagues from University of Wollongong and use their 3D printing technique based on the well-established welding technology to 3D print a test component which would have desired weld-like microstructure. We are currently in the process of examining the strength and molten salt corrosion performance of this component, but we believe that this development will accelerate adoption of molten salt-based energy generation and energy storage systems and thus contribute to the faster decarbonization of the power generation in Australia. So this was somewhat simplified example of one of our projects which we are currently working on.
We know that multi-scale understanding of materials in extreme environments is important and critical for safe operation of nuclear systems. That's why we put significant emphasis on knowledge transfer in collaboration with our industrial partners. Thank you for your interest in our research.